You know that universal frustrate, right? You step outside, bright sunny day, pull out your phone, and
Mhm.
poof, screen's basically unreadable.
Oh, absolutely. Or, you're inside, and that giant digital billboard across the way feels like it's trying to burn out your retinas.
Exactly. Displays are just everywhere, but getting them to work well, like everywhere, bright light, dark room without guzzling power, it still feels like a real challenge.
It really is. We stare at these things all day, but technologically, it's a tightrope walk.
Yeah.
Balancing visibility, power use, working indoors and out.
Mm.
Current tech struggles, though.
Hang on, because we just dove into this pile of really interesting sources you shared, and they're pointing towards something, well, frankly, something that sounds kind of bonkers. Okay, get
Haha.
this. A new type of display tech that uses,
Clay.
yes, like actual dirt, well, clay from the ground.
Wow, okay, that does sound pretty wild, like sci-fi stuff, but happening in a real lab?
Totally. And this deep dive is all thanks to some amazing research coming out of Chiba University in Japan. It's led by professors Nohisa Kobayashi and Kazuki Nakamura. They just published this stuff pretty recently, actually, in the Journal of Materials Chemistry, see.
Right, it's fresh research.
So, our mission today, figure out how on earth this works. How does a display made partly out of dirt
Hmm.
function? What's the science? And maybe the big question for you listening, what could this actually mean for the screens you use every day? Why should we care about screens made from, well, the ground beneath our feet? Let's dig in.
Okay, let's unpack it. So, at its core, this tech uses something called electrochemical stimuli responsive materials.
Okay, fancy words.
Yeah, basically just smart stuff that changes when you give it a little electric nudge.
Uh-huh.
A low voltage, and that change, it could be making color or producing light.
Right, so they react to electricity, they switch states, not just constantly on, blasting light. And the big leap here, according to the sources, is getting two key functions into one device.
Exactly. That's the breakthrough. They've made what they're calling a dual-mode electrochemical device. It can emit light luminescence like your phone screen, and it can also just change color, more like an e-reader, without necessarily glowing, all in one.
And the secret ingredient holding these two different things together is the clay.
That seems to be the key, yeah. The sources say they use these clay membranes. It turns out clay is a really effective way to integrate the molecules they need for both the color-changing and the light-emitting parts. Holds them together in the right way.
Professor Kobayashi apparently called it a game-changing concept.
Yeah, he emphasizes that it brings together these two, like, normally separate display ideas, glowing and coloring into one single device,
Yeah.
which boosts performance and makes it potentially useful in lots more situations.
Okay, so how? How does the dirt tech actually work? What are the nuts and bolts here?
All right, so you've got your basic electrochemical setup, right? Electrodes, so for the reactions to happen in, an electrolyte. The research highlights that putting the key active molecules directly onto the electrodes is better.
Okay.
Specifically, they use ITO electrodes, indium tin oxide, common stuff, transparent conductors.
Hmm.
Putting the active bits right there
Mm.
apparently gives higher efficiency, makes it more stable.
Right, stick the important stuff right where the electricity flows. Makes sense.
Yeah.
And the clay. Where does the actual clay fit in? What's it doing besides just holding things?
So they use a specific kind called smectite. It's a layered clay.
Layered.
Yeah, think like super, super thin sheets stacked up.
Yeah.
And smectite is great because it's good at ion exchange, things stick to it really well. That's absorption, and that layered structure is crucial. It doesn't just hold the active components, it actually stabilizes them, makes them work better.
Okay, stabilizes them. And what are these active components tucked into the clay layers?
Two main things, according to the sources. For the glowing part, the luminescence, they use specific europium complexes. Europium-3, technically.
Europium, I've heard of that. Used in screens sometimes for bright colors.
Exactly. It's good for vibrant light. They use a specific chemical setup with it to get the glow they want.
Got it. Europium for the glow. And the color change part.
That comes from something called heptoviologen derivatives.
Mm-hmm.
Let's just call them HV2 plus molecules.
HV2 plus Virgo.
These are the molecules that react to the voltage and produce a really noticeable color change.
Okay, so let me picture this. You have thin films made of this layered smectite clay. And inside the layers, you've got the europium stuff for light and these HV2 plus things for color. And it's all coated onto those transparent ITO electrodes.
You get it.
Then you apply voltage. They mention a specific number, minus 2.0 volts. What happens then inside those clay layers?
Okay, this is the really neat part, where the dual mode magic happens. Apply that voltage, and two things occur pretty much at the same time, very precisely. First, those HV2 plus molecules react electrochemically.
Uh-huh.
And that makes the film turn a really vivid cyan color.
Okay, cyan, bright blue-green. Got it.
Yeah.
What about the glow, the europium?
Right. At the exact same instant the cyan color appears, the light emission, the luminescence from that europium complex,
Yeah.
it gets quenched.
Quenched, like doused, turned off.
Basically, yeah, or at least dramatically reduced. So hit this with the voltage, and the display gets this intense color and stops emitting its own light. It flicks modes.
Whoa,
Yeah.
so it can go from acting like a tiny light bulb to acting like, well, colored paint, almost, instantly.
And reversibly, yeah. Controlled precisely by that voltage.
That is seriously clever. How do they synchronize that, make the light turn off just as the color turns on? Is it just a timing thing?
It's more integrated than that. The sources talk about complex interactions between the molecules right there in the clay layers, things like fluorescence, resonance energy transfer, and the interfilter effect.
Okay, FRET sounds complicated.
It is a bit, but
Right.
think of it like the molecules are interacting very closely. When the color-changing HV2 plus molecules get activated and turn cyan, they basically interfere with or absorb the energy that the europium molecules would normally release as light.
Ah, so the color molecules effectively tell the light molecules, hey, quiet down. We're taking over now.
Huh. Yeah, you could kind of think of it like that. It's a very controlled molecular conversation, helped by how close and ordered everything is within that clay structure.
And you said the clay structure itself, the layers, helps efficiency too. How does that work?
Right. Those layers, the space between them, the interlayer spacing, it actually makes it easier for ions and electrons to move around within the film. Which means the electrochemical reactions, the ones making the color and quenching the light, they just happen faster and more efficiently than they might in a less structured material.
So the clay isn't just a passive container. It's like greasing the wheels for the reaction.
Exactly. It's an active participant in making the whole thing work better. Pretty unexpected for plain old clay, huh?
Totally unexpected. Okay, so we've got this really smart tech. Using humble clay, low voltage, making a display that can flip between glowing and showing color. Cool science. But why does this matter for you listening? Where might we actually see this stuff, and what real-world problems is it solving?
Right, the payoff. This is where it gets really exciting, I think. Remember our first problem? Screens you can't see outside, screens that drain your battery.
Yeah, the everyday annoyances.
This clay tech aims right at those. First off,
Yeah.
energy efficiency.
Ah, the big one.
Absolutely. Because it runs on low voltage and doesn't need to be constantly blasting light, it could use significantly less power than typical emissive screens. Screens are such energy hogs. Any improvement there is a huge win.
Massive deal. Especially with screens on practically everything now.
For sure. Second point, the environmental angle.
Using dirt.
Well, using naturally abundant clay. It's potentially a much greener way to make parts of displays compared to relying solely on synthetic materials, some of which can be resource-intensive or tricky to dispose of.
Mm-hmm.
It's literally using the earth to build future tech.
It really is like turning things upside down. Tech from the ground up, literally.
Huh, yeah. And third, maybe the most practical benefit, adaptability.
Mm-hmm.
That dual mode thing means it works well in different conditions.
Okay.
Professor Nakamura really stressed this. He said, this tech bridges the gap, between reflective displays, think e-readers, great in sunlight because they use the light around them, and emissive displays, like your phone or TV, which make their own light so you can see them in the dark.
Right. Usually you have to choose. E-readers are amazing outdoors, useless in a dark room. Phones are okay inside or at night, but that glare outdoors, ugh. This clay stuff could do both well.
That's the goal, the promise. It can show that intense color, making it highly visible in bright light, acting kind of like a reflective display. And it presumably, by switching modes or adjusting, it can also work when it's darker. The key is having both abilities in one low-power system.
Okay, so I'm imagining a tablet I could actually, read comfortably on the beach, or digital signs outside shops that don't look washed out in the sun but aren't blindingly bright and power-hungry either.
Exactly. The sources specifically mention reflective tablets and digital signage as potential applications. It tackles those core issues: poor visibility of emissive screens and bright light, and the high power needed for emissive screens in general. It's like one technology solving two big headaches.
It really does feel like they found a super elegant way to combine two different screen philosophies. And the key was clay. Just amazing.
It really is. And they're not stopping there. The researchers plan to add other materials into the mix, try to enhance the functions even more. They want to make these displays even more versatile, open the door to, actual commercial products down the line.
Yeah. Professor Kobayashi summed up their big picture goal, right? Designing displays that are not only more sustainable, but also more versatile. Better for the planet, better for our eyes, whatever we happen to be.
A pretty fantastic goal.
Okay, so let's zoom out from this deep dive. What we've learned is that researchers over at Chiba University in Japan, they've come up with this new display tech. It's low voltage, energy efficient, super adaptable, and it's based on simple clay.
Right. By embedding these special light-emitting and color-changing molecules into layered clay, they've made a single device that can switch between showing bright color, like an e-reader, and potentially emitting light, solving big problems with screen visibility and power use.
It is just an incredible example of how basic material science, messing around with something as common as clay, can lead to something potentially transformative.
Absolutely. Makes you wonder.
It really does, doesn't it? I
Yeah.
mean, we literally walk on this stuff every day, and yet it might be the foundation for future screens. So here's the final thought to chew on. If something as ordinary as clay can unlock this kind of advanced tech, what other common, everyday natural materials might be out there just hiding revolutionary secrets, waiting for the right person to figure them out?